Now, anytime light hits a medium, some of it is reflected, but some of it passes into the other medium. So some of the light is going to pass down here. Let's actually call this theta 1 now. If this is theta 1, what would be a good symbol for this angle? Theta 1, because they're equal. Good. But now I'm going to call this angle theta 2. This angle does not have to be the same as the angle of incidence. This is called the refracted ray. What does the word refracted mean? It means bent. Refracted means bent. So the line that is transmitted into the new medium is going to be bent. It's not going to be the same size as the incoming light. So there's no reason to think that these two angles would be the same size. In this case, I've shown that it bends towards the normal. We're assuming that we bend towards the normal. So let's do that over here. Let's draw the refracted ray here, and let's suppose it's getting bent in the same way. Whoops, careful. Sorry. Oh, my mistake. All right, so you're looking at that. Okay, you're doing good. So again, we should call these two theta 1. Good. Now I should have said, remember this angle doesn't have to be the same as this angle. So how can we figure out how big this angle is? Do you remember what's the equation that relates these? Let me remind you of that one. Is that Snell's law? N1 sine theta 1 equals N2 sine theta 2. And clearly now the thetas don't have to be equal because the n's could be different. So this is much more complicated than reflection. In reflection, the two thetas are always equal. But the refractory angles don't have to be equal. In fact, they usually won't be. Now, I mentioned before that when you're doing reflection, it doesn't really matter whether you measure the angle with the normal or with the surface, because the angles with the normal are equal, and that means the angles with the surface also have to be equal. So you could say that two thetas are equal, or if you wanted to, you could say that two alphas. Either way, you get the right picture. All right, but it makes a big difference which angle you take the sine of over here. So is this supposed to be the angle with the surface or with the normal?
The normal.
Yeah, we just said that theta is always used for the normal. So that's why you might as well use the angle with the normal for reflection too. You might as well get into the habit of doing that. All right, so here, this has to be with the normal. It would be a big mistake to start focusing on this angle here with the surface, because that doesn't work in the Snell's law. Snell's law means that you have to be focusing on the angles with the normal. The question could still ask you for the angle with the surface, but you would figure that out by finding the angle with the normal from Snell's law. So Snell's law is based on that. And you were following that when you drew this picture. So if these two angles are theta 1, when you drew this picture, here's the refracted ray. This is going in through the surface into the new medium. And here would be theta 2. I said that it should be the same bending, so this angle should be smaller than this one. Although I didn't quite get that over here. I already drew the angle so small, it's hard to make it smaller. All right, so here's our theta 2, which I think is a little smaller than theta 1. Okay, and now what would be a good name for this? Well, maybe we could call this the transmitted light, or the refracted light. And then instead of calling this the outgoing light, now there's two rays of outgoing light. We can't just say outgoing anymore because there's the outgoing reflected and the outgoing transmitted. So maybe we could call this here the reflected light. And we could do the same in this picture. This is the transmitted or refracted light. The main point I wanted to make here is how many confusing lines you can end up with and how important it is to label all of them. Because again, it's not that hard to figure out what a line stands for, but it's very hard to remember that. So you have to draw a great big picture with plenty of room to label all of the light. Maybe most of the lines should be dashed for reference and just draw solid lines for the light. Maybe I should even have made it the surface dashed. I don't know. Oh, the surface is a real thing, so maybe it should be a solid line. I don't know. Maybe, I don't know, maybe a squiggle. I don't know, you can come up with something. All right, so the big idea here is a lot of this is just geometry. So it's important to draw a very clear picture and label all the parts. All right, why don't we go into more detail then about how to use this Snell's law, because because that very likely be on the test. But anyway, this is preparation for one of those homework questions where you have a bunch of different lines there. So I'll erase this table here. Let's do reflection and reflection. Reflection now. I think it's clear who's incoming and outgoing there because of the arrow, so I won't draw that. And call this theta 1. Another name for theta 1 is angle of incidence. Again, theta 1 is our angle of incidence. Okay. Do you remember what the name is for this variable n? This is the index of refraction. N is the index of refraction. So yeah, it doesn't stand for the normal line. N is our index of refraction. Why do they call it N? I don't know, maybe N for index? I don't know. But N is the index of refraction. Now, what does theta 1 represent?
The angle between the light and
the incoming light and the normal. And then theta 2 is the angle between the outgoing light and the normal. So what's the difference between N1 and N2? N1 is the index of the first medium. So every medium has its own index of refraction. Every medium, and remember the medium is just the stuff that you're traveling through. Every medium has its own index of refraction. So it's good to put in your picture, write N1 for where that's the index of refraction and N2 for where that's the index of refraction. So that's give us our N1 and our N2. So that's just a characteristic of the material. So every material has a different index of refraction. And you would look that up in a table or be given it. You should have a couple N's memorized, like the index of refraction of a vacuum, which is 1, and the index of refraction of air, which is also 1, because the air is pretty close to a vacuum. So that's something we're expected to have memorized. We're expected to have memorized that a vacuum and air both have an index of refraction of 1. If we have time today, we can explain why that is, but right now we'll just memorize that. Now you can see that in optics here, we're always dealing with acute angles. The angles here are always less than 90 degrees. So let's focus on an acute angle. For an acute angle, as theta gets bigger, what happens to the sine of theta? Do you remember that from trig? When the angle gets bigger, does the sine get bigger or smaller? Bigger. Good. We can remember that from our unit circle idea. Remember that the sine is the y-coordinate on the unit circle. Well, as the angle is getting bigger, we're moving counterclockwise. Well, moving counterclockwise moves us to a bigger y-coordinate. So there's a positive relationship between theta and sine of theta. This is one of the good reasons why it's good to use sine and not cosine here, because the cosine would have an inverse relationship. It's much simpler to have a direct relationship between theta and the sine of theta. Theta is big, the sine of theta is big. So let's say that N2 is big. That is, it's bigger than N1. Let's say that N2 is bigger than N1. What does that tell us about theta 2? Bigger or smaller than theta 1?
Bigger than theta 1.
Like this?
N2 is bigger
Than N1. Should this theta 2 be bigger or smaller than theta 1? Because you can see it couldn't be an equation this way, right? If this term was bigger and this term was bigger, how could these be equal to each other? This is a good example of how it always is important to write down your thought steps. If you just say in your head that this is bigger, that seems plausible. But if you write down big, big, then it seems like the equation doesn't work. This can be bigger than N1 because this is smaller than theta 1, and that's how these two sides can be equal. So is there a direct or an inverse relationship between N and theta? When n gets bigger, what happens to theta?
It's smaller.
Yeah, so when light is moving into a medium with a greater index of refraction, theta gets smaller. What does it mean when theta gets smaller? It means you're bending towards the normal. Remember that theta is the angle with the normal. So do you think theta 2 here was bigger or smaller?
Smaller.
So is n2 bigger or smaller?
Bigger.
Yeah, the reason that we're bending towards the normal here is that this medium must have a bigger index of refraction than this one. I said before that air and vacuum have an index of refraction of what?
1.
And I should also have mentioned everybody else's index of refraction is bigger than 1. Everybody else, that's worth having in your notes. Everybody but air and vacuum has an index of refraction that's bigger than 1.